Hello and welcome to what's new presentation of NVH in version 25.1.0. Starting with ANSA. A new tool is introduced in Statistical Energy Analysis Ribbon, which is designed to streamline statistical energy analysis. The Load Case Assistant facilitates the creation of load cases tailored for statistical energy analysis. It is possible to generate basic entities for boundary conditions and frequency domains effortlessly, and the load case is transferred to the ANSA database. A new solver for statistical energy analysis is implemented in ANSA. Key metrics such as energy, velocity, pressure, modal density, modes and band, modal overlap, and wave number can now be computed directly within ANSA, eliminating the need for external solvers. Results are integrated within ANSA and can be saved for future reference or to be reloaded if necessary. In Optimization Tool, it is now possible to add correlation as objective type. When selecting it, a new column appears, in order to define the reference curve in .csv format, based on which the correlation will take place. The type of the correlation metric can also be defined among available functions for comparing curves in Meta, for example, CCF, WIFAC, FRAC, and many more. Regarding Optimization/DOE Setup Tool, Screening Algorithm is now available. Using Screening Algorithm, it is possible to cut candidate design variables down to a manageable number of significant ones, with which a better design can be achieved, using the same amount of time and computational resources. Sensitivity Analysis, Morris Method, is performed to reveal how sensitive a specific response is to each design variable. Moving to Meta. It is now possible to build multiple FRF assemblies in the same database. The components and connections can be retrieved from a common pool. The respective assemblies can be built from analytical simulations, from measured transfer functions, or can be even hybrid, comprising of analytical simulations and measurements as well. It is possible to create and compare assembly variations, modify connection types and properties, change the component properties, and conduct what-if studies for different FRF assembly configurations, in order to compare results. There is a new tool available in the NVH ribbon tab, the Modal Transfer Functions. If a model is loaded along with its mode results, it is possible to select a node and calculate the point mobility of this node, having predefined the degrees of freedom and default values for damping. It is also possible to select a second node, and the transfer function between the first and second node can be calculated. It is now possible to calculate on-demand diagnostic results, participations, animations, during NVH calculations from modal response. Calculations are applied directly to the loaded model. Regarding Modal Response Tool, the modal displacements can now be read from Abacus ODB files in frequency and transient case, setting type equal to 5 for modal displacements in load case section. The results from modal response and the solver are here compared and found line on line. Rayleigh damping definition is now supported in Modal Response Tool. Material damping can be specified using Rayleigh damping, which combines mass proportional and stiffness proportional damping. The mass proportional damping is proportional to the mass matrix and simulates the effect of the material moving through a viscous medium. It primarily affects lower frequencies and is defined by the damping factor A1. The stiffness proportional damping is proportional to the stiffness matrix and reflects the material's internal dissipation mechanisms. It influences higher frequencies and is defined by the damping factor A2. These factors can be a single value or can be defined through a table. In Fast Solution 103, so far it was possible to output energy participation per component modes. But the energy per component as a sum over all modes is a point of great interest, as this information can facilitate the identification of the component which is causing a certain system mode. For this reason, we have added a new output from Applicis, which provides the energy participation per component. This output request is supported by meta and kinetic, potential, and total energy per component as a sum over all modes can be read. Regarding FRF assembly, it is now possible to define a control volume, a sub-assembly, within an FRF assembly and request transfer path analysis for this control volume. Pressing the Control Volume button, it is possible to select from the available components, the ones that will constitute the control volume and transfer them in Added Components section. Prerequisite is that the components which constitute the control volume have to comprise a single connected assembly. It is then possible to request transfer path analysis for the control volume. This is the result of requesting TPA on the control volume. Pressure transfer paths, point mobility, connection forces, transfer functions, and transfer path fractions are calculated. A universal joint, also called a universal coupling or U-joint, is a joint or coupling, connecting rigid shafts whose axes are inclined to each other. It is commonly used in shafts that transmit rotary motion. The U-joint connector was available in NVH console and now it is also supported in META and FRF assembly. Regarding structure-structure interaction connector or SSI, the SSI connector is already available in META and FRF assembly. The SSI connector connects structural components through a point cloud and can be any FE representation. Connections of any representation can be solved in Applicis and output the modal matrix. This DMIG matrix can now be used to define the SSI connector in FRF assembly, instead of the Nastran bulk file that was used previously. This feature provides flexibility to the definition of SSI modeling. Moving to the demonstration of new features, let's start with ANSA and statistical energy analysis. Switch to SEA ribbon and load the model. The model is organized in SEA subsystems. Switch to SEA subsystem draw mode to observe. Press the load case button and select Assistant. Press right mouse button on boundary conditions to apply a new constraint or a new load. Select to apply a power source. Select the subsystem where the boundary condition will be applied. And define the tables for flexure, extension, and shear power. Press OK. Define a new frequency domain. Set the domain type as third octave and define the start and end frequency. Press Apply and OK, and the load case is defined. Regarding the SEA analysis solver, it is possible to calculate key metrics directly within ANSA, without needing external solvers. Energy, velocity, pressure, modal density, modes and band, modal overlap, and wave number are available. The plotted results in ANSA can be overwritten, and it is also possible to output the results in H5 format and save them in a folder. Press Calculate and after a few seconds, calculated results are displayed. It is possible to navigate to all available results through the fringe label. Identification and color bar options are also available. Moving to Meta, Model Transfer Functions tool is implemented in NVH Ribbon in order to facilitate the setup of the modal response tool. Prerequisite for using the tool is to have the geometry and the results files. Load the model and open Model Transfer Functions tool in NVH Ribbon. Three different types of setup are available. Starting with the driving point, we will set up and calculate the transfer functions of the excitation nodes from the selected degrees of freedom towards the same degrees of freedom of the same node. Select an excitation node by picking or typing directly the ID, a coordinate system, if available, and the respective degrees of freedom. Under Options, it is possible to define the frequency range, the variable that will be calculated, and modal damping. A name can also be defined. Activate Setup and observe the result in modal response. Note that if all necessary files do not reside in the same folder or they do not have the same name, a window will pop up to define the files. In case a coupling file is necessary, but is missing, it is possible to be calculated at that point. Here the respective coupling file will be selected. Modal Response tool opens, and the load case is set up. A load is applied on each degree of freedom and a response is requested on the same node and degree of freedom. Close Modal Response tool and press Calculate. Three curves are calculated, as expected. Select a cross excitations type and the tool will calculate the transfer functions from each selected degree of freedom of the excitation nodes towards each selected degree of freedom of all excitation nodes. Observe again the setup in modal response. For each selected degree of freedom of the excitation node, x, y, z, a transfer function will be calculated for all defined degrees of freedom. Close Modal Response tool and press Calculate. Nine curves are calculated, as expected. Select excitations to responses type and the tool will calculate the transfer functions from the selected degrees of freedom of the excitation nodes towards each selected degree of freedom of the response nodes. Select a response node, a coordinate system if available, and the respective degrees of freedom. Observe again the setup in modal response. For each selected degree of freedom of the excitation node, x, y, z, a transfer function will be calculated for all defined degrees of freedom. Close Modal Response tool and press Calculate. Nine curves are calculated, as expected. Select a curve from the list and press right mouse button. Observe that NVH insights are now available through modal response calculations. From the plots list, it is possible to calculate participation fractions and animation on top picks. or participation fractions for the whole range. It is also possible to select a certain pick directly from the curve and apply NDH insights as well. Thank you for watching. Stay connected.